one step is to step away from Poiseuille flow. Poiseuille flow, you learn this in, for example, in the convection course that I teach every other fall semester. Poiseuille flow exists in the limit of very slender ducts. So Poiseuille, in fact, Dr. Poiseuille figured out this formula for the flow with friction through a duct because he was interested in blood flow through capillary blood vessels. Capillary, you know what the capillary means? Capilla, Latin, Italian. It means hair strand, the hair. So blood vessels as slender as the hair strand. That's what those things are. Well, those are not the pipes under your floor here. In pipes with, let's call it palpable diameter, the flow is obviously faster, and it flirts with being turbulent. So in most places, it is turbulent all along. So what is the corresponding list of ahas if the flow is turbulent? So for turbulent flow, and here we're talking about fully developed, the method remains, but the formulas become slightly different. Luckily, they become simpler, but that's to see very, very soon. What do I mean by fully developed turbulent flow? The following, this is what happens, which is normally not taught in the fluid mechanics that people teach you. Here's the duct, meaning this duct. And the mass flow rate, m dot, comes in. And it does not flow with a profile that's easy to draw. In fact, as I said, most people don't know what happens right after the entrance because nobody has access, meaning unlike the dentist, to look in the mouth of the duct. In the beginning, the flow encounters friction against the walls. And that means that it develops boundary layers. And those boundary layers, like all boundary layers, thicken downstream. And they merge somewhere here. In the beginning, the velocity profile is slow down near the wall, and then unaffected in the core, and then slow down again. So what was, let's say, uniform flow in the beginning becomes non-uniform here. And eventually these boundary layers meet by eating up the core. They meet at a distance downstream called entrance length. So if this is x and this is x equals 0, the entrance length is the length along which the flow is developing. It is changing from one x to the other. And then downstream of the entrance length is the so-called fully developed length. The sketch that I made refers to laminar flow. This is the profile of Poiseuille, which means fully developed laminar. This is fully developed laminar. Next comes a joke. you ask your colleagues the difference between laminar and turbulent, they'll tell you that turbulent is complicated. No, not in today's series of punchlines. The equivalent drawing for turbulent flow I will not draw the round cross section. It's simpler because, okay, the turbulent flow, it has eddies, few large, many smalls, like the wheels under the steam locomotive. Some of those are big, others are small. They'll roll together. In fact, never mind. Even when you fall down the pavement and you scrape yourself, basically at the interface between the pavement and you, there's some rolling goes on, rolling of your tissue, all right? Time averaged, the so-called boundary layer, this is the boundary layer, grows linearly, just like that. Not in a curved fashion, linearly. And it is a linearity with a universal aspect ratio. The universal aspect ratio is that the x, meaning the extent of the entrance length, is approximately, but almost exactly, 10 times the diameter. And so, yes, downstream of 10 times the diameter, you have fully developed turbulent flow. So in future work of yours, using flow through ducts, you're, of course, empowered with formulas for pressure drop in fully developed laminar flow, pressure drop in fully developed turbulent flow. Make sure that your pipes are longer than this capital X. The formula for capital X laminar is complicated. You'll find that in the textbook. This other one is not. You see that? And yes, the entrance length for turbulent flow is relatively short because the pipe diameter is not very big. But you get the idea. You have to be careful with the meaning of the words that you employ or other people throw at you. So what's different? Different is the flow regime. And I start with this formula for the penalty of interest, which is the pressure drop, which is proportional to the pumping power, assuming that this m dot is specified. And the pressure drop is 4 times the duct length divided by, and we'll stick to round tubes at this point, and then the friction factor, and then 1/2 rho mean velocity squared. The mean velocity, here it is, or in turbulent flow, the profile is relatively flat, so the mean velocity is not much smaller than the centerline velocity. And the mean velocity is the mass flow rate averaged over the cross-section of the tube. The cross-section is pi over 4 d squared. And you get the idea, first of all, that you substitute in here m dot squared over rho squared, and then pi over 4 squared, and then d to the 4th. And then the friction factor, in an earlier lecture, about 3 lectures ago, I showed you the so-called Moody chart. the origin of which was in the work of Nikuradze and Prandtl in the 30s. For turbulent flow, this F is a constant that depends on roughness. The roughness of the internal surface of the duct. Okay, so you're lucky. F is a constant. Therefore, the pressure drop is equal to the mass flow rate and then the duct length, mass flow rate squared, duct length, and then you divide by diameter to power 5, and then a product of constant factors called C prime. This C prime is a constant, meaning that it's the same C prime for every design that you come to contemplate. What?
Why do we use the D? I forgot, like the D with the.
Oh, this is when I said that I'm talking about a round duct.
Yeah. Why is that? So that's
it's the same thing as here.
So
yeah.
First.
Yeah. It's the same as this drawing here. A round duct. But what I teach about the round duct is the same as for any duct, provided I use the hydraulic diameter in place of capital D. That's the reason why people use hydraulic diameter terminology. And that means that in contemplating the same problem as here, the problem was about the pressure drop between this entrance and these two exits, or in the other direction, these two entrances and this single exit. That pressure drop is the sum of two pressure drops. One is called delta P1, and the other one is called delta P2. And when you add these two together, you obtain an aggregate formula, which is C prime. This constant comes in front. M dot squared comes in front because you have M dot squared at this end, and M dot over 2 squared coming out of the branches or the tributaries. So you end up with M dot squared, and then a group that depends on geometry alone, L1 over D1 to power 5 plus 1 over 4, and then L2 D2 to power 5. Of interest, of course, is the factor that depends on how you make the drawing, and I call it the resistance in turbulent flow. Here you see, again, the 4 variables. The 2 constraints do not change. The external constraint is, as before, L1 to L2. The flow volume is pi over 4, and then D1 squared L1 plus twice D2 squared L2. And the rest is history. You, yes?
Last section, you derived that same equation, but it was dependent on L over D to the power 4, not 5. And then last lesson, it wasn't M dot squared, it was M dot.
Well, for laminar flow, it was M dot, not squared.
Oh, so right now.
Today, for turbulent flow, it is, I made this point a few days ago, lectures ago, for turbulent flow, the so-called resistance, which is the across divided by the through. It's not delta P divided by m dot. It is delta P divided by m dot squared. Don't ask me why, but that is another way to distinguish between laminar flow and turbulent flow. And once again, most people think that turbulent flow is complicated to death. That is actually not true, according to me. But you see the let's call it the beauty in the joke. You see it right here. The formula has become simpler. The entrance length is child's play. It's an aspect ratio. That's what it is. And you begin to appreciate the value of thinking of complicated things in a time average manner. Yes. I commented on variety and diversity in the previous lecture. Well, exhibit the freedom of averaging those variations, discrepancies, the personalities of the flow. Just average them in your head and try to see as I called it, the thread of the river. All right. And so after this, the method of analysis is identical to what you've seen before. The search for easier access consists of trying to minimize this flow resistance. In 2 steps. Part 1, assume that the lengths are known. And then you minimize this resistance subject to the internal size constraint, because there these diameters are appearing. So subject to V constant, you discover that there must be a ratio of d1 over d2, which turns out to be 2 to power 3/7, which is almost like writing square root of 2, which is something that's probably like 1.3 something, a number of order 1 greater than 1. Just like in my drawings, you see. Not in this drawing, because I should have made it more like this. All right, so, and then in part 2, while absorbing this kind of idea, meaning substituting it back into the expression for the object of the game, you minimize the resistance, which was minimized once already, this time subject to the external flow constraint, and you get the second aspect ratio, which turns out to be 2 to the power 1/7, which is very close to 1. And you get results of this type, and you become even more confident in your expectation that a flow configuration, even if complicated at first sight, comes with a particular design that recommends itself as offering greater access. 1 degree of realism, 1 set of formulas with which to make the drawing. But of course now in your bag of tricks you have 2 solutions to this problem. The one that I taught last lecture, the one that meaning for laminar flow. This is now for turbulent flow. The formulas change a little bit, but the message is the same. And why not travel in this direction of, let's say, direction toward the greater realism? I will sketch a few milestones of my own, questioning and then problem solving. And frankly, I forgot where if I publish these next steps. But they come from questioning. I told you the other day, you walk through the jungle, look behind you in order to make sure your footprints are lined up in the proper direction, so you don't end up in the mouth of the beast. Let's try to make the drawing be more realistic. The vascular design of blood flow is not with branches or tributaries that make right angles. They make angles that are not right angles, Well, what should those angles be? And so by solving the same problem, but this time for, a drawing with 5 variables, not 4. There's L1, D1, L2, D2. There's this angle here. Let's call it alpha. And by the way, working this problem is not as menacing at first look, because you already know that when you fix all the variables except the duct thicknesses, you will get a particular aspect ratio for D1 over D2, which is 2 to 1/3 for laminar flow, and you just found out 2 to 3/7 for turbulent flow. So this new problem has only 3 variables, not 5. Every time you figure out that the beast is not as dangerous at first looks, you should feel good about the fact that you are maybe a little bit, you're kind of clever, okay, or lucky. Anyway, so as I recall, the alpha, I'll call it optimal. Optimal doesn't mean best, it means selectable. How do I know that? Because I question the meaning of the word. To opt is to select, to choose. It doesn't mean you're choosing the best. You have no idea whether I do. I know what the best is, but I don't recommend anybody to believe me, okay? But you're opting all the time, okay? So selectable, recommended by this analysis, is 75 degrees for laminar flow. This particular statement is in the textbook, in the text, because I told you I don't remember where I published it, but anyway, that's in the DCT book. For turbulent flow, you see here, turbulent flow is like if laminar flow is the older brother, turbulent flow, which is a more recent subject in fluid mechanics, is like the younger brother who's copying what the bigger boy was exhibiting. This looks like a round number, 75 degrees. Turbulent flow, the best angle of bifurcation or pairing is 50 degrees. So now you have the answer to this, how the drawing happens in this new direction toward greater realism. Another step beyond what I just put here is comes again from questioning your own cleverness. Adrian, why do you keep making drawings that have only 2 branches or two tributaries? Why not 3 or 4 or 7? The question is, why dichotomy? Dichotomy means something that's cut into 2. This is cut, and this is 2. You've heard of this computer tomography. That's a technique of creating images, one slice through the animal body after the same slice. So you make many slices, and in each slice you have a picture. So to cut is this in Greek, okay? The beginning here is like in all the, I would generalize, all the Indo-European languages means 2. Yeah, why? Question mark. And, meaning you can contemplate the mother channel being followed by n branches. And I think this is a problem that I'll assign on Wednesday. And then you discover that for laminar flow, the easiest access for this single m dot out of this mustache is 2. So n should be 2 for laminar flow. I mean, fully developed laminar flow. For the other one, such as the river basins, the number is 4. But the river doesn't branch out, the delta doesn't branch out this way. I'll show you how she does. So 4 for turbulent. In fact, all these flows are bathing a page, an area. And if let's say the mother channel that collects its tributaries is this way, then for turbulent flow, the 4 tributaries are, they come from both sides this way. And this is the way, this is a poor man's drawing of what you see when you look from above on the rain plane. Every plane, which is the low area of the river basin, meaning downstream from the mountains, that is where you see the design best, is like this: an area with a thick channel fed by rivers of the next smaller size. The next smaller size, from large to small, those are approximately, meaning statistically 4, corresponding to a mother channel. Yes? The point is, yes, flow regime matters, but the result is, once again, the secret to you, which is that you know to expect the existence of a simple answer, because it's not difficult to remember 4, what the difference between 4 and 2.